Okay, in this presentation we want to look at a new concept, the concept of acceleration, which is listed here as being a rate of a rate, and I'm going to talk about what that means. But it's worth noting that the first real systematic view of motion was carried out by a guy named Aristotle, and you've probably heard of Aristotle. He's very famous. He is famous as a Greek philosopher from ancient Greece, and he's also famous as the father of biology. So he's considered the progenitor of one of the major branches of science. He also wrote a lot about physics, and specifically he wrote two books, one of them called Physics, and that's actually where the name physics comes from. It's the Greek word for nature. And so Aristotle wrote a book called Physics, and he wrote another book called Metaphysics, which is basically means beyond nature. You might think of that as being supernatural, but not like ghosts and vampires and stuff. It's supernatural in a very different way. His book on metaphysics is really weird, but his book on physics is interesting because he really did analyze a lot of things about motion, but unfortunately, most of the things that he came up with, most of his ideas were incorrect. Now, they weren't crazy, they made sense, but they just happened to be wrong. Now, a lot of these views that Aristotle had that were incorrect, they were unfortunately accepted by the Catholic Church. They were incorporated into church dogma, and this was back in the days when the Catholic Church was the only Christian church around, really, and it had really absolute political power. And so you would not go against the Catholic Church in those days because bad things would happen to people who did. And when the Catholic Church said Aristotle's our guy and his views are right, people didn't question that. And so Aristotle's views were accepted for a very, very long time until they were finally upended by the work of a guy named Galileo Galilei. Now, you might have heard of Galileo. He's pretty famous now. He was the person who decided to actually employ the techniques of the scientific method and test the views put forth by Aristotle. And when he made those tests, he found that those views were simply wrong. Now, in particular, Galileo was very interested in studying the concept of motion. And so he did a lot of experiments with things that were moving. And in particular, he was interested in the motion of falling bodies. So if you drop something, how does it move? And, if you drop something from a meter or so high, it hits the ground in less than a second. It's very, very fast, and it's hard to analyze that motion because it happens so quickly. So he did something really clever. He built these long inclined planes, basically these ramps, that he had cut polished grooves down the middle as sort of a channel for balls to roll down. So he was able to roll balls down these long ramps. And so instead of taking, a half a second to reach the ground, they would take maybe 5, 6, 7, 8 seconds, and he could measure how they moved with time. Now, another advantage that Galileo had over Aristotle was the fact that Aristotle didn't have a clock. It's really hard to do experimental physics if you don't have an accurate way of keeping time. And Galileo had a clock. It was called a water clock, and it was basically a bag filled with water that had a valve attached to it that would let water drip out at a steady rate. And so drip, drip, drip. Each drip was like the tick of a clock, and he could see how far his balls moved per drip, and he could measure out and analyze their motion. Now, through his experiments, Galileo managed to come up with a new idea, and it's an idea that's obvious to us today, but until someone had figured it out, it wasn't obvious to people. And so let's recap what we know so far. So we've seen how we can describe velocity, and velocity is the rate at which position is changing. So it's the displacement over time, or the change in position over time. It's the rate at which position is changing. And through his measurements, Galileo found that for falling bodies, the velocity of the body was constantly changing too. And this was a new idea that he came up with, the idea of acceleration being the change in velocity with respect to time. Now, here was the thing that was really brilliant about Galileo's discovery. He found that not only was the velocity changing, It was changing in a regular pattern that could be described by a mathematical relationship. And so math would be able to be used to analyze this kind of motion. So just as the position can change with time, so can the velocity. Things can speed up, they can slow down. The velocity can change. The rate at which velocity changes is called the acceleration. And so we can have a definition here for acceleration. The average acceleration is simply the change in velocity over the change in time. And we can note velocity is a vector. That means that acceleration is also a vector. Okay, now we can look at the units of acceleration. And we know that acceleration is delta v over delta t, the change in velocity over the change in time. Now velocity has units like meters per second, some kind of distance over time. It could be miles per hour, whatever, but usually we're going to be looking with meters per second. And then the time, so we've got delta v over delta t, meters per second over seconds. And of course, mathematically, this second is technically in the same denominator that that one is, so I can group these seconds together, and when you multiply seconds together, you get seconds squared. And so the normal way that you would write and say the unit for acceleration would be meters per second squared. But this formulation here actually gives you maybe a little bit more idea about what it means. So let's say that we have a ball that we're holding up, and so it's at rest. It is not moving at all, and then I let go so that it falls. It turns out that everything that falls near the surface of the earth falls with a rate of about 9.8 meters per second squared, or 9.8 meters per second every second. Just to make our life a little easier, let's guesstimate that. Let's call it 10. We'll round up to 10. So we'll say that things fall 10 meters per second, that's their acceleration. So what does that mean? Well, this guy's dropped from rest, so it's got zero velocity when it starts. And after 1 second, it's going to have 10 meters per second. That's going to be its velocity. After 2 seconds, it's going to be going 20 meters per second. At 3 seconds, it's going to be going 30 meters per second. So every second it gains 10 meters per second in velocity. That's the change. There's a change of 10 meters per second velocity every second. So that's what we mean when we say 10 meters per second, or more commonly, 10 meters per second squared. Again, it's just the rate, how much velocity change you're getting every second. Now we've looked at some plots of position versus time. We can also plot velocity versus time. So let's consider motion among one dimension. So we're going to consider motion that's constrained to be moving along the x-axis. And we're just going to look at this graph. And what does this graph tell you? What's going on? We can see that the velocity starts with zero velocity, then it increases, and then it decreases back to zero, and then eventually it becomes negative. And so what does it mean that the velocity is negative? That means that at this point it's actually changed direction. And so if you were looking at this graph, a lot of people tend to view them like position versus time graphs. They mix them up in their head. If this were a position versus time graph, if I had, x versus t, we've already talked about how, if I've got x versus t, at the top here, that's where the velocity is zero. And so a lot of people will make a mistake and they'll think, oh, up here the velocity is zero. But really, where's the velocity zero? The velocity is zero there, and the velocity is zero there. And so what's happening here is there's a change between the velocity increasing and it decreasing. And so what's actually zero there, we'll see, is the acceleration is zero there momentarily. But the main point that we want to make is that you don't want to mix up velocity versus time graphs with position versus time graphs, because they indicate very different things. So when you see these graphs, keep in mind when you're talking about the velocity and when you're talking about the position. Now, if I look at 2 points, say a point right there and a point right there, 2 points on a velocity versus time graph, they will be some time interval delta t apart, and there'll be some difference in velocity, delta v. And if I draw the rise over the run, delta v over delta t, that's going to be the slope of that line. And so that tells us we know that the slope of that line, delta v over delta t, that is just the average acceleration. So I can note that the acceleration is going to be the slope of a velocity versus time graph. And so that's a very important idea. And of course, just like we did before with velocity, we can take the limit as delta t goes to 0, and that tells us that the instantaneous acceleration is going to be the derivative of velocity with respect to time. And of course, what that means is that we can calculate the instantaneous acceleration by taking the derivative of v with respect to t, and that's going to be synonymous with the slope of the tangent line. So if I want to know what the instantaneous velocity at that point right there is, if I know what the function is here for velocity, I can simply take the derivative and plug in the value. Or if I can get the tangent line and take the slope of that tangent line, and that will give me the instantaneous acceleration at that point. But the key takeaway from this slide is that to calculate the acceleration, you just take the derivative of the velocity. So let's look at another velocity versus time graph. We can look at some of the qualitative features. So first of all, the first thing that we can notice is that it starts, here's t equals to 0. It has a positive initial velocity. So it doesn't start with 0 velocity. When I start my stopwatch and I start taking data, this thing's already going. But we can see that its velocity is getting smaller, it's decreasing. And here, at this point, it is 0. So at this point, the thing momentarily stops, and then the velocity changes direction, and it's going in the negative direction. And then it comes a point where basically the velocity is not changing. The acceleration is 0 from here to here, so I've got a constant, steady, negative velocity, and then it's going in the other direction back to 0 where it stops. And so that becomes the way of tracking this and understanding how to interpret these velocity versus time graphs. You look at the slope, and you look at the values, whether they're positive or negative, and that tells you the information that you get from that graph. Now, in the very first slide of this presentation, I said that acceleration was a rate of a rate. And I just want to mention what that means, because we've already talked about how velocity is the rate at which position is changing. But acceleration is the rate at which velocity is changing. So if I write down that a is equal to the derivative of velocity with respect to t, that's the rate at which velocity is changing. But that's the same thing because velocity is equal to dx dt. And so that's the rate at which position is changing. And so this is the rate at which another rate is changing. It's a rate of a rate. And of course, you hopefully will recognize that as the second derivative. And so if I'm given x of t and I want to find a, I just need to take the second derivative. So a is equal to dv by dt, but that's going to be equal to the second derivative of x with respect to t. And of course, if you're given v and you want a, you differentiate once. If you're given x, you can differentiate once, which will give you the velocity, then differentiate it again, which will give you the acceleration. Mathematically, this works just like we've seen before. So if my acceleration, the instantaneous acceleration, is the limit as delta t goes to 0 of delta v over delta t, I can simply break this down into x, y, and z components. And as I take the limit as delta t goes to 0, I end up with derivatives. And I can write that the derivative of the x component of velocity with respect to time, that's just going to be the x component of my acceleration, and so on for y and z. And so again, basically, all this means is that if you want the acceleration, the instantaneous acceleration, you just take the derivative of the velocity vector. So we have the a vector is going to be equal to the dv vector dt, the derivative of velocity with respect to time. That gives me my a. So in this slide we have a nice summary. We have the average acceleration is simply delta v over delta t. The instantaneous acceleration is dv by dt, the derivative, and the instantaneous acceleration will also be the second derivative of position. Let's look at an example. This is similar to one of the examples we worked previously, but this kind of repetition is maybe kind of useful. So the position of a particle is given by some x of t, which is equal to 2 meters per second squared times t squared. Notice I'll have seconds squared here. The seconds squared, when I plug in a number there, will cancel, leaving me with meters as my units. Position, we expect to have some kind of units like meters, so the units all match. And so I've got 2 meters per second squared t squared minus 5 meters per second t plus 10 meters. Now again, this is just in the x direction. I could have brackets around this in an I hat, and I could have another term with j hat, and another term with k hat. Then I could have a full r of t, but you do it exactly the same way. So to make my life a little easier, I'm just going to consider motion along x. And the problem is to find the average acceleration over the time interval from 1 second to 3 seconds, and we want to determine the instantaneous acceleration at the time interval 2 seconds. So how are we going to do that? What do we have? What is x of t? X of t represents the position of the particle at any point in time. That's what it says, the position of the particle, and this t means its position as a function of time. So how do we get the average acceleration? Well, what's the definition of average acceleration? We know A average is equal to delta v over delta t. And what is delta v? Delta v means the change in velocity, final minus initial. And so we want to find the velocity at 3 seconds and then subtract from that the velocity at 1 second. So if we're given the position as a function of time and we need the velocity, how do we do that? Well, we just differentiate this guy. So we're going to differentiate this guy, and then that'll give us the two velocities we need to calculate our delta v. Now, the next thing it asks is the instantaneous acceleration. How do we do that? Well, that's going to be taking the derivative of the velocity, or the second derivative of the position. And so I'm simply going to differentiate this twice, and that'll give me the acceleration as the function of time, and I'll just plug in my 2 seconds. So let's look at how to do that. So we wanted to find the velocity first, and so we know we can simply take v of t is the time derivative of our x function, and when you differentiate that, you get 4 meters per second squared t minus 5.0 meters per second. And once you have that, you can just plug and chug. V of 3, V of 1. So here I plug in 3 seconds for t there, and here I plug in 1 second for t, and then I just subtract those, and then I divide by the time difference, and this is from 3 seconds to 1 second, so that's my delta t, and this guy is my delta v. So there's my delta v on top, there's my delta v below, and so I just need to calculate those and do the division. So what we have here is our velocity function, which we got from differentiating our position function, 4 meters per second squared t minus 5 meters per second. I plug in 3 seconds, and I end up with 7 meters per second. 4 times 3 is 12, minus 5 gives me 7. So if I plug in 1 second, I can say that I'm going to end up with 4 times 1 gives me 4 meters per second minus 5 meters per second. That leaves me with a minus 1 meter per second. And so I just plug those values into my formula for the average acceleration, and when I do, I get 7 minus a minus 1 divided by 2, and that leaves me with 4 meters per second squared. Notice in the numerator I've got meters per second, in the denominators I've got seconds, so meters per second over second gives me the right units, and that would be my answer, 4 meters per second squared. that would be my average acceleration over that particular time interval. Now, we want to calculate the acceleration, the instantaneous acceleration. What's the acceleration at 2 seconds? And if I take this guy here, what I'll find out is that v of t is equal to 4 meters per second squared t minus 5. If I take the derivative of that, the t is going to go away. That constant term will go away to 0. And so I'll end up with just 4 meters per second squared. That's what I found on the other side. But what does that mean? It means that the acceleration is constant. The acceleration is not 4 meters per second times t. It's not varying with time. In this particular problem, the acceleration was constant. If I had had a different function, it necessarily wouldn't be constant. But this is the approach of how to find that out just by taking these derivatives. And so what have we done? We've seen how to calculate the average acceleration, which is delta v over delta t, and we've learned how to calculate the instantaneous acceleration, which is the derivative of velocity with respect to time.